So, so that was just simple concepts about component reliability. Often we're interested in system reliability. You may have seen these concepts, you may not have. So system reliability is a function of the reliabilities of the components comprising it. Okay? So you have to now think of, in addition to component reliabilities, what combination of component failures lead to system failures and which do not. Okay? And this is, again, something that the end user determines, right? What they consider failure of a system. If you think naively, you think all systems are series systems, right? You might think that, but then if you think about it, like, for automobiles, sometimes we have failures, battery dies. You just replace the battery. You don't necessarily think of it as a system failure, okay? So each combination of failed components that leads to system failure is called the failure mode of the system. And then to determine the failure modes, one needs to understand the connectivities between components. So pretty straightforward concepts, right? So if either of the components leads to system failure, components are said to be connected in series, okay? If the failure of both components are required, we say that they are connected in parallel, okay? So this is the block diagram representation that you might have seen before, that on the left-hand side, we have a series system, 1 and 2. Sometimes one way to think about it is there will current flow from one end to the other. Or if I send a packet from one side to the other, will it get to the other end? So if both 1 and 2 are working, then the system will conduct. Otherwise, it will not. So it's a series system on the left-hand side. On the right-hand side, it has, so to speak, two pathways. So, and this can be easily generalized for many components in series on parallel, right? So you could have a large number of components, and you can see what the system reliability in that case is. Okay. So just to understand basic concept, the reliability of a series system here would be less than the reliability of even the least reliable component. Okay. The reliability here would be more than the reliability of even the most reliable component, right? So if you think of it as two generators working in parallel, one is enough to support the load, then this is a very reliable system. And then here we have loss of reliability because it's a series system, because two things have to work. Let's say you have a generator and then you have a voltage converter. Okay, if either one of those fails, then you don't have power. So failure modes are just these combinations, right? One fails, two fails, or 1 and 2 both fail, this will fail. And here, there's only one. Hang on. If both 1 and 2 have to fail, for the parallel system, for the system to fail. So the question I have now is, I'm sure you've seen this before. Actually, let's just go through a few slides before we do that. Okay. So sometimes I call it system topology, where this block diagram representation. And since all systems need to survive, in the case of a series system, the reliability of the system is the product of the reliability of individual components. So that goes without saying. So this is where the probability of system, reliability of the system being less than the least reliable system in this case comes, because both of these numbers are less than or equal to 1. Okay. And for parallel system, we just do some basic calculations. We say reliability of the system is 1 minus one system fails, another system fails. So the only time system fails is when both of them fail, and then we go 1 minus that. So this is the only time system survives is both of them are surviving. No, the only time the system fails is when both the components have failed. Okay, sorry for that. So in series system, reliability system is the product. In parallel system, 1 minus this. So system component 1 fails, component 2 fails. Both of them have to fail for the system to fail. Okay. So yeah, it's some of these things you have seen before, I'm sure. But let's see what I have here. We'll talk about that later. Okay, so a few things. One is, should we prefer series systems or should we prefer parallel systems? And because this is, in some ways, you can call it a simplistic type analysis, right? So let's have a more involved discussion about, should we prefer, if we have a choice, let's say. Right. So number one, we may not have that choice, right? So if there are two different components that have to work with each other, well, there's nothing we can do, right? The other thing with having parallelism, yes, we understand that it increases reliability, is that sometimes as human beings, we tend to be less careful about maintenance if we have backups. Okay, so there's many layers to this discussion, right?
Fail-safe is with respect to the parents.
Right. So if it's just a matter of having it there and guaranteeing you some certain reliability, yeah, parallel systems are good. But oftentimes we see that as human decision makers, when we have redundancies, we tend to not be as careful with those systems, right? And oftentimes you would see in engineering practice, you will have two redundant systems, and since they are in disrepair because one system is working, they will not repair those other systems or start cannibalizing parts to make one of the systems work, right? So that's one thing that I saw quite a bit. So yes, in general, we have increased reliability because we have fail-safes, but it has these more second-order effects that people don't always maintain such systems well. Okay. Another example for series systems is that aircraft where, the outcomes are severe. If something bad happens, there's a lot of things that have to work right. You have stringent inspection protocols, and you have a lot of laws and oversight for that reason. So you can compensate somehow that way.
So there are two wings of airplanes.
Hmm?
Series.
Huh?
Two engines of airplanes.
Yeah.
Series.
Well, it's not as simple as that. So, because when you have two engines in an airplane, most airplanes can fly with one engine, but then you have two things. One is you have asymmetrical thrust. So the plane wants to go a certain way. And then the other engine is not only not producing power, it's also adding a lot of drag, right? So, and some planes cannot take off on one engine. You have to have, there's a whole bunch of conditions associated with it. So this is a gray area whether we call it failure or not. But obviously it's an emergency. You will land. Yeah. So this type of representation, so there's a couple of ways, right? So we also do fault tree analysis, and we do this kind of representation of system topology. This type of is very easy to visually inspect if the system is working or not, right? So that's the benefit of this type of approach. For example, I can say that if there's a path from left to right, this system is working. Otherwise, it's not working. Okay, so we see that component 1, 2 are in series. They are together in parallel with 3, and then that subsystem is in series with 4. So reliability of the system can be calculated by converting it into a sequence of subsystems connected in series and parallel. Okay, so we realize that this is in series, so the reliability will be the product of the reliability of these two components. This is in parallel with this, so we will use the parallel component formula for that, and then now whatever answer you get, you just multiply that with this, and then you get the answer, right? So here just I show you pictorially what we can do. And then we multiply these reliabilities, and then we get the analysis, and that's pretty simple. Okay, so now we go to another way of doing system reliability analysis is fault tree analysis, which is again, it has the same information as the block diagrams, right? So we're not adding or subtracting information; it's just a different way of looking at it. So system topology can be represented using a fault tree. So fault tree propagates the failure events using the Boolean operators of AND and OR. Okay, so the failure events of working or non-working components, you represent them with a binary state of 1 and 0. Okay, so AND gate acts as an intersection operator, means that both have to be 1 for it to report a 1, while an OR gate reports 1 if at least one of the inputs is 1. Okay, so now you see where the parallel series will be represented here. Okay, so just standard elements of a fault tree. You have a basic event, you have an AND gate, you have an OR gate, you have a terminal event, and your lines show the flow of events. So earlier I showed you the fault tree of 4-component system. We can represent it in this fashion, right? So 4 basic events, which is component 1 fails, component 2 fails, component 3 fails, component 4 fails. Components 1 and 2 feed into an OR gate, signifying that failure event will be transmitted even if one of the components fails. Okay, so 1 and 2 is through an OR gate. Let's go back to our fault tree here, or the block diagram here. They're in series. Okay, so we were propagating failure events. Okay, so now we go here and then we say, okay, 1 and 2, if either one of these fails, the failure event will end up here. And that and 3 are combined through AND gate. So both of them have to be yes or 1 for it to be propagated. And then again, that subsystem was in series with component number 4. So there you go. Right, so they both represent the same information, so no problems there. Fault trees have the advantage that they can easily be implemented in a system simulation tool. Whenever I've coded fault trees, I've found it easier to do this because it's a little bit more logical. Of course, there's software that does this for us, right? We can import system topologies into software. We're almost always back working within a few days. So again, this availability number also makes sense. So there's quite a few things I want to say about this, right? But before I do this, I want to go back to our discussion here to any of these systems, right? So let's look at this case where of course, you see this in undergrad and you've used this many, many times. Of course, if the systems get a little bit more complicated, you have to think about it. But you can do this. What is one assumption that you see here that should bother you by now? We assumed that the component failures are independent. Are component failures independent? Why not? And what makes component failures dependent?
One component fails for some reason, like it might also fail.
Yeah, so we can envision many scenarios where, so heat is one. If there's a power surge, or the flow rate is too high in the Venturi, or user error can cause cascading failures, right? And the other thing is that if one subsystem fails, which was in parallel, that increases the load in the other system, and that also fails. So component failures are not independent events more often than not, and that has to be built into our calculations, right? So obviously that changes our calculations. So we cannot multiply probabilities anymore. Probability of this event multiplied by the probability of that event gives you the joint probability if and only if the events are independent. If they're not independent, then you have to find joint probabilities of these events, right? So, of course, you need to know that. If you are doing time-dependent reliability type analysis, that will have to be built into your system. If you need a joint distribution, you have to have a joint distribution. And you can't just say the marginal distribution of this variable and the marginal distribution of this variable, and then lo and behold, my system is perfect, except you haven't taken into account the correlations or the dependence between random variables. So that is one caveat to this basic analysis that I kind of wanted to bring out. And the same thing I wanted to say about this example that we have of availability and mean time to failure. What is limited here? What is the limiting factor here? What do you miss when you do this kind of simplistic analysis? If you look at the data carefully, we see that there's some skewness in the data, right? Sometimes the system runs for a long period of time, and sometimes it fails even initially in very short period of time, right? So averaging these days of operation to get mean time to failure can be misleading, okay? Because people might be led to believe that I can run for 117 days uninterrupted for the most part, right? I mean, they understand it's a variation. There will be variation around it, but they may not always appreciate that. The data should tell you that, right? So we looked at some metrics that you could come up with. So we talk about minimum failure-free period with a given probability, right? So you can, since you have all this data, you can come up with more statistics. You can come up with more interesting ways of doing it. For example, you could say, give me with 90% probability how much I should expect nonstop operation, right? And then you can do the calculations like that. With 90% probability, you'll get at least 50 days worth of operation. Okay, so that's useful to people. And then we've also proposed or suggested for systems engineers that we really cannot talk about reliability in simplistic terms, right? Like availability and MTTF and things like that. We have to have a collection of metrics, because whatever metric you choose will miss something or will be harder to interpret or something like that. So how about having a collection of metrics for defining the reliability of time of systems that operate for a long period of time, okay? And collection of metrics that we talked about are minimum failure-free period, degradation information. So we know that this system here is probably not performing the same level of this system here. Can we build other metrics into this? So to distinguish that, this mirrors everything into one number. We're saying, no, look at this carefully and see what it's trying to tell us. Are you actually getting that MTTF? Is the system in the initial phases the same as the system at the later phases? So on and so forth, right? So I suggest, creating a set of metrics and reporting all of them, not just these two, okay? And then the last thing I wanted to do today was do a case study, but I do want to take a 5-minute break before we do that. Okay. So can we stop the recording for 1 second?
I'll just check.
We're going to take one more short break and then continue from there. So we did this example a few minutes ago, and that gave me an opportunity to think about the limitations of availability in MTTF that we just talked about, right? So these are simplistic analyses. Large organizations, especially for smaller components, will still use MTTF for their components, right? And also at the same time availability, but these are limited as we talked about, right? So we again look at the data that was presented earlier. So you see this system here at the beginning seems to have longer success times than towards the end when it fails pretty often, right? So the mean time to failure, if we calculate using this, just the first 8 operation periods, will be very different from what you got in the subsequent operational periods. And similarly, availability is also misleading, right? That availability says 97.2% time of whatever we got in the last slide. 97.3% is time the system is expected to work, but we don't know what time that is going to happen, right? So we thought about this problem a long time ago when I was working in the reliability engineering field, and we had a conference publication where we said, okay, the biggest problem here is that we're not thinking in terms of wish list as to what are the things that we essentially want our metrics to do, right? So as a guy who does decision analysis as much as I do, I said, okay, let's ask the decision maker, what is it that I want? Okay, so we will just do one thing here. I'll just make it appear one by one. Okay. So we created this list of desiderata for repairable system reliability. So obviously we're not talking about not repairable systems, we're talking about repairable systems. That's why the whole concept of availability and MTTF comes. Okay. So we said, what properties should such a metric or set of metrics have? Okay. So first and foremost, we talked about this in the last slide, should model transient behavior. Okay, so I have a repairable system. I want to come up with a metric that generalizes MTTF and availability, and I should be able to model transient behavior, like what happens in the beginning, right? New systems will act differently than steady state systems. So what happens in the beginning? I want to know. They should also model steady state behavior. So I tried to distinguish between the two. What new systems may act differently than steady state. So, okay, we'll have a metric for this and have a metric for that. Or have a metric that does both simultaneously. Should describe repair frequency. Okay. So, the bad thing about availability is that a system that fails every hour, but only fails for a few seconds, will have a high availability, right? But it's so inconvenient, it obviously misses the point of getting, defining the reliability of such systems. Okay, so again, let me start the stopwatch. So should describe repair frequency, should not be too high. It should describe a measure of performance starting from an arbitrary time. So steady state, transient, wear out life, we should be able to describe those. Should consider initial and final repair costs, right? So obviously availability is just looking at failure and non-failure. Okay, well, if failures are easy to repair, I don't care. If failures are expensive to repair but are quick, that's a different problem than take a long time to repair but they're cheap. Okay. Should also describe technical obsolescence. So we talk about wear out life. That is a different concept. Wear out life says the system itself has degraded, that it actually needs constant repair. Another thing for long-term systems is that, that's just a old technology. Like cell phones will go through cycles of these technology, not cycles, so will actually reach technical obsolescence that, they just won't work with the modern software or would not be able to load websites and so on and so forth. So you should be able to capture that. You should help identify the best repair strategy and so on and so forth, right? And then finally, determine the total period of operation. So once you come up with a metric like this, then you have some guiding force as to what is it that you want. And we thought that this was pretty exhaustive. I mean, of course, you can think of other things, but we thought that this will capture it more than just the two commonly used ones, right? So Desiderata, I really like this approach. This is what they use for decision analysis too. What do you want your decision-making method to do? There's a lot of decision-making methods. There's weight and rate. There's AHP. There's top. So there's a lot of methods, right? But decision analysis is the only one that met all the desiderata, that you could make decisions under uncertainty, the trade-off behaviors were captured, and you could do value of information. You could not do value of information in AHP for that matter, right? So we come with the desiderata, and then we sort of mark out, like, if we use these metrics, do we address the desiderata? Okay, so we said, okay, time to first failure. Okay, so report like on average time to first failure. We report it in addition to the MTTF. So that takes care of the transient behavior. First failure on average happens at this time. Mean time between failures. Minimum failure free period, MFFP with a given probability. So you say with 60% probability, I can guarantee a 200-day failure free period. With 98% probability that I guarantee a 30-day failure period, 90% of the time your thing will be above. So we're basically just doing the percentiles of the distribution that we had for the failure-free operations. Number of failures, right? So first we look at planning horizon. So you say, okay, what is the planning horizon? Is this going to continue on forever, or you have a retirement date? Once you have a retirement date, then you can talk about things like number of failures within the planning horizon, or expected number of failures within the planning horizon. Okay, so that captures other aspects of system failure. And then finally, we did effective age. So when I was a grad student, I developed for, when you have systems that you're constantly replacing and repairing components for, eventually now you end up with a system with some used, some new, some old, some half-working components. Okay, well, how do you define the performance of such a system? You can say it's working, so it's good. Oh, not really. Some things are old, some things are new. There's obsolescence issues. My reliability function is all off. My performance function is all off. So in one of the works that I did, I can send again citations to anybody that's interested, is that we looked at inverting the reliability function in age years. I said, okay, I can specify the performance of the system in years as opposed to in some number that 0.7, 3.78, whatever that means. We said this system, after all these repairs and remanufacturing, is expected to work like a 5-year-old system, right? The oldest component may be 10-year-old, the newest component could be brand new, but overall, once we look at all the different performance characteristics, we can cover. So there was a mathematical way of doing that. So that's what effective age is presented as one of those techniques. And then you have average repair time, and then the cost of the system, right? So, and then we see if we are able to address the desiderata that we had. Okay, so in this case, we thought, okay, well, if we have these 8 metrics, we basically covered this. And again, the claim is that if you had a few metrics, you will not be able to capture all these things, right? So if you are working with a system where you can come up with more desiderata, come up with a list of things that you would like to report about that system so you can fully understand the performance of the system. Again, when you're buying systems from other manufacturers or other people, they will always try to push for, people take advantage of metrics, right? All the way from manufacturer suppliers to everywhere. People take advantage of metrics. So this way you make sure that there's no real way of taking advantage of a metric. If you have this, gives you a full picture of the thing. So this was something that we proposed, and that's something that I guess would be interesting for you to take away. All right. So finally, the case study that I promised. Okay. So the idea of the case study here is that we will try to integrate, at least I will try to integrate the things that I have covered and the kind of problems that we work on in the academic side of things. Okay. So this discussion that I'm going to present is based on this paper that I co-wrote with 3 other co-authors. Came out in 2010, varying lifecycle links within a product take-back portfolio. Okay, so this work was a continuation of some work that some other students had done and I had done during my PhD, and I continued to work on, which is what we call product take-back systems, with the idea that you're going to reuse and repair some of the components and then reinstall them into the system that you're considering. So you are encouraged to go over this publication in detail. I have not worked in this area for some time, so I may be rusty in some of the topics, but it's still a very interesting topic to me, and I would love to restart research in this area. So what the work did is that we developed a decision-making model where we utilized concepts from pretty much everything you saw. So we used concepts from reliability engineering, we used concepts from optimization, we used concepts from decision analysis, and we used concepts from environmentally conscious design. Okay? So environmentally conscious design is design philosophy which actively considers reduction of the negative effects on the environment. And this is an enterprise level model so that you can develop it and use it as a manufacturer to enhance customer satisfaction and also optimize profit. So one of the aims of this kind of work was that we can do a single attribute type analysis. We can say, okay, reduce environmental impact. We've talked so many times about revealed preferences and stated preferences. People will say they will buy environmentally benign products, except when the time comes they buy the product that they want. Okay. So as a manufacturer, again, being environmentally conscious is a good thing, but we see that most manufacturers don't follow through unless there's profits to be made. A lot of times they're interested in the halo effect. That, there was a time when I think some companies were talking about putting a solar cell on the roof of a car so we can recover some energy and all that. I mean, the total power they could make was, 10 watts or something like that. So it was pretty much just for gimmicks and not really helping the cause. So here we wanted to make sure that we also consider profits. So if whoever is considering implementing a model like that would also be able to make profits. So of course, sustainability considerations in design are increasing, right? Because of legislative constraints and customer satisfaction reasons, right? So customer satisfaction reasons is because we do see people who are, at least some part of the population is environmentally conscious, and they would go the extra mile to do what's right for the environment. And then there's also legislative pressures, right? So if, this data might be old, but a very small minority of the waste that goes into the landfill is electronic waste, okay, in terms of weight. But in terms of environmental impact, it's a substantial portion of the landfill waste. So if you throw organics into the landfill, that really doesn't harm the earth, right? But if you put chemicals, electronic stuff which has all these chemicals and metals that are bad for the environment, then you have bad environmental impact. So legislation came. A lot of European countries, and I think some U.S. states were also thought about how to minimize these electronic waste going into the landfill, how we can recover value from it. So, of course, it's an added constraint, right? So I'm designing a system, and I'm solving an optimization problem, and I add a constraint. Okay, now let's also think about environmental considerations. Of course, my solution will change. I will not do things the same way as I was doing before. But it's a great test bed for applying system design principles, right? So I felt like working on this problem taught me a lot, because I could do decision analysis, and you will see that we did quite a bit of decision analysis in here. I could do design optimization. I could do what-if analysis. I could do design, redesign insights from having run this model. I could think about computational issues, right? So programming. We collaborated with a faculty who was a computer scientist, and they were looking at how we can solve some of these complex problems using distributed computing principles. So that resulted in an IEEE publication where we presented a distributed pool GA, pool genetic algorithm, which can find solutions. We can actually tolerate failures in the distributed computing networks, right? So it just is such a rich test bed that you can keep adding layers and to it. And finally, design for assembly and disassembly. So some students that worked in this area moved to design for assembly and disassembly. So it's a good thing to talk about product take back and reuse, but if products are not designed to be disassembled properly, then they're wasting a lot of time. So there was a comparison of PCs versus Apples, and Apple computers were notoriously difficult. These are not my words. These are somebody who was a PC recycler. The Apple computers were notoriously difficult to disassemble and reuse, versus PCs were free for all. You can easily do it, right? So their operation was mostly in reusing PCs, not Apple computers. Okay, so I found this to be a very, very interesting test bed. Okay, so how do we do environmentally conscious design? Many ways you can do it, right? You can have better manufacturing processes. Okay, that makes sense. I can look at the energy consumption in manufacturing. Some manufacturing processes are very energy intensive. Okay, so we can think of better ways to manufacture products. We can do better design, right? So I can design something that lasts a long time. Okay, well then, if it lasts a long time, the customers won't send it to the landfill. It'll be reliable. It wouldn't need a lot of repairs. Another way we can do this is environmental impact during use is minimized. So all these Energy Star appliances that we have. So refrigerator that almost runs all the time, or an air conditioner that runs almost all the time. Those things, if I just make them reliable, so I may not touch the manufacturing process. I just somehow figure out a way to make them more efficient, I should say. Then over the lifetime, I use less energy. So that's how you can be environmentally benign. I can make biodegradable products, so I can do product take back and reuse. Okay.
So then we're looking at modularity.
Yes, so that's sort of that's more modularity is one, definitely. A better design, you should say, like you use a different design architecture of the product, right? So a product that's easier to assemble and disassemble, that's where it comes from. And that's actually why we used electronics, because electronics, the way we were looking at personal computers, they were easy to disassemble and reuse. Okay, so which of these do you think we proceeded with? Yeah, you would think that, but what about products that are already there, right? So if there's millions of products already in the marketplace that were based on bad design, there's nothing you can do, right? So it doesn't work retroactively. Of course, that's a good thing to do moving forward. And then something that we can also do is that, so all these are feasible techniques. That's not what I'm saying. I'm saying that you can do manufacturing processes improvement so that going forward you save money while making the product. Some products have most of their energy consumption in the use phase. Cars, for example, right? So the amount of energy they use during their lifetime is way, way more than what is used in making them. Okay, so it's the better benefit is had when you minimize their emissions or energy usage while using versus while manufacturing. So there's many factors that go into it. Okay, so redesign to make a product biodegradable or otherwise environmentally benign is very difficult and does not work retroactively. You cannot do anything about the things that are already there. So both of these are good techniques, but what about all the millions and billions of stuff that we've already sold? So we looked at product take back and reuse because it focuses on already existing products. It's already there. What can I do with it? Okay. So of course you can't start collecting products from customers. They may not give it to you. Okay, or it might be logistically difficult. It's not easy to get things back from people. So you have to think about creating an ecosystem where customers are encouraged, or in some cases obliged, to return the product for an upgraded product, right? So what we say is that the manufacturer in this case sells the product as a service. Okay, so you don't say that I own this computer, you say that I have leased this computer from the manufacturer, and they have promised that if every year and a half they'll give me a new one and take this one away, right? So that they're selling me service, not a product. I mean, this is already done for a lot of products. Like, if you have copiers and photocopying machines, those are actually leased. They're not necessarily used, bought by the end user. And then what I recover, I can reuse, recycle, or remanufacture. I can directly reuse it if it's in good condition. I can recycle it, means that I can shred it, melt down the material, recover the material, and reuse the material. Or I can repair it. That's also good. That if a minor error exists, I can fix it. So the benefit is reduced environmental impact, increased customer satisfaction, better market coverage. That's the goal of this kind of analysis. Okay. The challenges, of course, is that there's a lot of things you have to do. You have to talk about take back. You have to talk about incorporating stakeholder preferences, right? Manufacturer wants to make profit, but this guy wants a fast computer, that guy wants an environmentally benign computer, and this guy wants a utilitarian computer.
So, won't this method, this product paper and reuse be time consuming?
Yeah, it has to. Yeah, it is time consuming, right? But so a student had actually done the entire analysis. So if you have, let's say, I mean, logistically it's time consuming, right? But if you think about, I have to make something from scratch versus I can just reuse a component. Even if I can just do it for a small number of them, that saves me a lot of time and effort.
Yes.
Right. Yeah, circular economy is a new term right now, right? Yep. So challenges are take back, incorporating stakeholder preferences, finding best reuse decisions, because how do you optimize decisions for each component, and how do you address computational issues? So we try to do all this at once, right? So here I have just a graphic. From the top, you say raw materials go into material processing, which goes into manufacturing, assembly, and then your final component, which goes into a product, and then somebody uses it, and then disposes it. Okay. So we say, okay, after use, we take it back. Okay. Well, we can also collect, disassemble, and dispose it. So what's the benefit? Well, we shouldn't do that. If we do that, then we have essentially made a new product, a new component, right? We can, when we collect it, we can put it back in the supply chain, we can reuse it, or we can remanufacture it. So that's like remanufactured, but just like repair. So we, at this point, we disassembled it, we remanufactured something that needed fixed, maybe resalt or something, or add a new chip, and then we send it back to the customer. Okay. Or we can recycle it. So when we disassemble it, we can shred it, go through the recycling process of melting the material, and we go back to the raw material stage. So We can make new, in which case, obviously, nothing has changed from status quo. In fact, we may have made it worse because we spent time and energy collecting it. I guess somebody would have collected it. We can direct reuse, we can remanufacture, we can recycle. And you can already start to see that there's relative advantages to this, right? So, or advantages or disadvantages. This seems like this is the worst thing ever, making new products from an environmentally conscious standpoint, right? Because if you make new, then the raw materials don't come from recycling, they have to be mined. So there's mining operations, and somehow we create the raw materials that go into, or create the raw materials that go into the manufacturing process. Then the next worst is recycling, that, okay, we pretty much went all the way up to the supply chain, and then we covered materials, and we went there. And sometimes people have done calculations that it's not even worth, because the environmental impact of recycling is more than just getting it straight from the ground. Sometimes people have found that the material mix, so there were some studies on material mix, how many different types of materials you use. So if something is an alloy that is made up of multiple things, or if you have a part that really is hard to disassemble, which has copper and aluminum and this and that, but by the time you shred and melt it, it's useless.
So, like, what is reman?
So remanufacturing is
Remanufacturing.
yeah. So remanufacturing is the next better option, where you say, okay, well, I'm not getting down to the individual metal. I'm using parts and components to repair the system back, or the component back. And reuse seems the best from a sustainability, environmentally conscious perspective. And the reverse order plays in the performance criteria. The reuse will be the worst, remanufacture may be slightly better, recycle will be almost as good as new, and then new would be new. Okay. So that's the trade-off right away. You see a component for each component. And then the next point that I like to make here, or we have liked to make over time, is that whole product reuse versus component level reuse. Okay, so what should we do? If you have an original product, you can throw it away and make a new product, or you can reuse it. Okay, what are the limitations of this approach? The big limitation is that you end up with only two products, either new or reused. Okay, reused. Somebody used it for 5 years, and then now you have it, a completely used product. Only two products are possible. But if I disassemble this and then get down to parts level, now I can do a whole spectrum of things, right? I can do everything is new. Some things are new, some things are old, and you go from there all the way to completely reused product. Of course, your decisions that you have to make for each component increases, but the benefit is manifold, right? That oftentimes we can identify critical components, and that I did a lot of work in that as well. So the effective age metric I talked about looks at critical components. This also looks at critical components, just upgrade those, right? So let's say if I take a computer and I change the processor and the RAM, I have improved it substantially than if I just change the power supply and the tower. So the benefit is that I can focus on individual components, and because I have this whole spectrum of different types of products now, different levels of products now, I can also target different customers, right? So somebody wants latest and greatest, you give them the new or the almost close to new. Or my dad, who's very utilitarian, you give them something that barely works, and they're happy to have it, right? Because there's also price differential along the way. So numerous products are possible, various attribute levels can be obtained, better customer satisfaction, and less amount of expense expertise needed, right? So if you start reusing things, that takes almost no expertise. Many computer recyclers in America would tell you that they just reuse pretty much everything because it's not worth fixing. But some things, if you have a little bit more ability, you can fix it. But if you want to recycle, then I guess now you have to start shredding and have to have a whole processing facilities and things like that. But you have combinatorial explosion. You have your optimization problem becomes very difficult to solve. Okay, I'll talk about this. Now, the other aspect of this is multiple life cycles. Okay, so I mean, we like talking about planning horizon. We don't think that time repairable systems really work without planning horizon. So we have planning horizon, and here, let's say there's some measure of performance that goes down over time, right? So we say, okay, let's look at a baseline that we guarantee. As soon as you push it up, you are forced to replace the system at this point. You basically bump up the performance to here, and then it starts falling again. And then as soon as it hits this line, you again do some repair or upgrade, and you go from there, right? So what you've done here is that as soon as you start limiting the lowest performance you will tolerate, you by definition introduce multiple life cycles, right? So it's a pretty trivial concept. If I only want the latest computers, I will be replacing it every year. There's nothing wrong about that. But as a manufacturer who's trying to sell that service, I have to think about that. Okay, there's people who want computers every year. What do I do? Okay, we just generalize a lot of things from what had been done earlier. We said we can modify the life cycle lengths as opposed to this fixed. We can say, you know what? We can choose, because it's possible that one customer would have allowed this product to go down in reliability, but we say, you know what? The system level optimal solution is that you give me back your, because I have better benefit going on by giving it to some other customer, right? So it's a sort of, you sell it to the right customer at the right time. You perform different levels of upgrade. So sometimes you perform a major upgrade like we show here, and sometimes you perform a smaller upgrade. And the number of life cycles is also unclear because planning horizon is here. Here you could just say, okay, one life cycle is this many years. You divide the planning horizon by that number, you get number of life cycles. Here it depends on, because it's a very complex problem because products are coming, they're getting disassembled, some of those components are going to some other customer, and then you want to make sure that everybody has something that they need at the right time. So life cycles are different, like I said, and the upgrades are different, and it just flows from the basic discussion I showed earlier. Okay. All right. So I have a meeting, so I have to make sure that I don't go too long. All right. So now, problem formulation, right? So we solved it as a multi-objective optimization problem, which you have seen before. There are three objectives of price, reliability, and environmental impact, which are optimized simultaneously. Okay. So we're interested in making sure that we get a Pareto front over these three attributes. And then we have price is summed over all life cycles and the profit margin is added. Reliability is minimum reliability in all life cycles, right? So we assume that that's what the customer cares about, that in the life cycle, my reliability should not go below a certain level. And then environmental impact is summed over all the life cycles, right? So we say, okay, well, whenever you make something, you manufacture it, recycle it, you incur some environmental impact, we add it together. Okay. Subject to this constraint that design decision for each component is fixed. So either you make it new, reuse, remanufacture, or recycle it. Okay. Or some order, but either way, you only make one decision for each component, and this is the length of life cycle. So, all right. So we continue on, and then we segmented the markets as opposed to saying that there's whole. Because the idea here is that if it's free for all, goes to every single customer and I optimize that level, then collection becomes difficult. So I say we bind customers into four kinds of customers. These were Technophiles, people want the latest and greatest. So like they would prefer higher reliability, they're willing to pay more, and they don't care about environmental impacts. Utilitarians, they don't want to pay more, they want something that barely functions, or tolerate something that barely functions, and they also have similar, and they're not crazy about the environment. Greens are people who are crazy about the environment, they're willing to pay more, and they're willing to tolerate lower performance. And then neutrals are people who are in between all three, right? People, let's say, average people. So we use the multi-attribute utility function formulation. We did cover it. Did we cover multi-attribute? Oh yeah, we did. Okay, so did cover it. Let me cover it in this course. All right. I'll just change that on the fly, which you're familiar with. So no issues there. Okay, and then so basically you see this is a three attribute problem. We have cost, environmental impact, and reliability. So for each customer, for each customer type, we will do three different single attribute utility function assessments, and then also their scaling constants associated with each attribute. Okay, solution of the optimization problem. How did we solve it? The optimization problem was solved using an NSGA2 algorithms, which you saw earlier in one of the lectures. It generates a Pareto front over the attributes, and the optimal solution was chosen from the front for each market segment. So here's the link to that paper. You've already seen that before. And here's the Pareto fronts, right? So since there's three attributes, it's hard to show. So what I have here is well, first I show the three-dimensional Pareto front. Hang on. Here, and then I show two-dimensional slices. Okay, the solution is basically it pushes it until you hit no simultaneous improvements are possible in all the attributes. So here we have environmental impact and cost. Here we have reliability and environmental impact, and then here you have reliability and cost. Let's see if I can see that over there. Okay, and then we show different color codings for different number of life cycles. So let's delve deeper into this. I'll just show you the best solution for each customer group. So for technophiles, guess what? We have a lot of life cycles, as expected, because they want something new often. The lowest reliability we ever hit, it was 0.91. So since they are constantly replacing, constantly reusing, constantly replacing their systems, they also spend a lot of money, cause a lot of environmental impact, but they have a lot of reliability that comes out of it. And they're replacing their products every year. And this was all built in, like, if you actually clicked on the solution, you will find, okay, for technophiles, every time the processor was new, every time this was old and this was new, and so on and so forth. So most components were new for technophiles. If we go down to greens, almost nothing. So they are holding on to the product for 5.5 years each. This was a 10-year planning horizon. Their price is much cheaper because they're mostly working with used, most likely something that these people handed down. Environmental impact is much lower, and then the reliability, the minimum reliability is also much lower, right? So and that's their game always. They're trying to minimize this. They're willing to pay more. They're willing to tolerate lower reliability. Their utility is very high, but in all this process, the manufacturer makes money, right? So we have a profit margin associated with it, which I'm not showing here. But the whole idea is that they come up with their leasing model where they are able to target each customer based on their environmental preferences and so on and so forth. So with this case study, we showed how different engineering tools come together to create a product stewardship system. So that's my thing with systems engineering. I think you will need these tools People spend quite a bit of time drawing models and creating wish lists in systems engineering. I think when it comes down to doing systems engineering, you pretty much need those domain independent tools. You should be able to think of demand of a product. You should be able to think of customer needs assessment. You should be able to set up optimization problems and solve them. You should understand decision making. You should understand uncertainty and reliability engineering. Okay, plus a few other concepts that Dr. Singh will cover. We covered these things here, and then just to come back to the model, very helpful for manufacturers to create a system that best satisfies customers and also maximizes profit, right? If they're able to target each customer segment. Work also highlights what you said earlier, the benefit of modular architectures, right? So reuse remanufacture requires easy disassemblability. Circular economy requires easy disassemblability, and systems analysis helps us think about these things in a grand scheme of things, put a lot of tools together and create solutions for the society. So that covers my presentation. Here's my contact information. I guess the most relevant one is the email. So make sure you contact me if you have any questions, and I'll be happy to answer any questions today or at a later date if you send them via email. Right? Thank you for your attention and thank you for your time.
Sir, would you tell me how you collected the data? Did you request it from company or you did some random data case study?
There was a lot of literature survey that was done by a prior student for each. So they actually broke down the data into so literature survey basically is like doing investigations into how much environmental impact and cost is incurred in making each component and so on and so forth, right? And then for environmental impact, you break it down into different activities, and then you use some standard tools like SimaPro and Gabby. I don't know if you're familiar with those. So there's some tools available that can help you calculate the total environmental impact in millipoints. So if you look at how much how much ozone depletion potential is there, how much of this kind of heavy metals is there, how much carbon dioxide is generated, how much. So they have come up with a way of combining all that into one measure of environmental impact. So the students in our group prior to me being there actually did all that analysis and created that data. Yep. Okay. Thank you.
Thank you.